This is the screencast for section 1.6, example 4, reflecting even functions. Alright, so example 4 asks us to prove, there it is, the dreaded P word, that the graph of an even function remains unchanged when it's reflected across the y-axis. So in my head, I'm visualizing an even function, which is the same on the left and the right of the y-axis. So if I reflect it over the y-axis, yeah, the left side's going to be in the same spot as the right side was, and vice versa. But I got to prove this. Well, my given information in this case is the fact that it's an even function. And I know that an even function that means that f of regular x has the same output value of f of when I plug in the opposite of x. Okay, so far, definition of even functions is that f of x equals f of negative x. They have the same output regardless of whether you plug in the positive version or the negative version. So how does that relate to reflecting across the y-axis? So to reflect a function over the y-axis, you make the transformation f of negative x. So the input changes signs. Well, now, in conclusion, since a reflection over the y-axis results in f of negative x, and even functions f of negative x equals f of x, a reflection of an even function will have the same outputs. Now, I admit, your book does a way better job of explaining it than I do, a much fancier, more mathematical way, but they have they have the luxury of being able to form those words and edit them, etc., before they are going to publish them. In this course, I will expect you to accurately represent the logic of a proof. Your words should have meaning to them and substance, but it does not have to be textbook quality. This is a good example of not textbook quality. This is a good logic, it makes a connection, and it does prove, it leaves no room for any kind of alternate example, an example that contradicts my proof. The now try problem for example 4 is number 33. It says prove that the graph of an odd function is the same when it's reflected across the x-axis as it is when it's reflected across the y-axis. So I'm going to make a note to myself, this is different than the last proof. I'm not proving that a reflection is the same as the original. I'm proving that a reflection across the x-axis, so opposite of f of x, so a vertical change, is the same as f of negative x, a reflection across the y-axis. So this is what I'm trying to prove. Okay, well, the given information is that this is an odd function. So since this is an odd function, that means when I plug in the opposite value of x, I get out the opposite y value of what I started with. Oh. Okay, so that is actually exactly what I'm trying to prove. I just need to put that into words to make that connection. So since an odd function has opposite input resulting in opposite output, a reflection across the x-axis opposite output and a reflection across the across the y-axis opposite input are the same. So basically I took the definition of an odd function and I translated it into a translation. So instead of this meaning an odd function, the definition of an odd function, I took the left side and translated that into a opposite input, which means a reflection over the y-axis. And then I took the right side and translated it into the opposite output, which means a flip over the, or a reflection over the x-axis. Therefore, they have to be equal.